Hello and very good day to everyone. So this is our integrated project to develop a plan for producing a methanol, and this is our group members.
Assalamualaikum. My name is Muhammad Nukadi Adli bin Mos, student ID 22012011. Today we start with the introduction for the methanol production plant design. In this project, we design a methanol plant using basic chemical engineering concepts. The process includes chemical reaction and physical steps like heating, cooling, and separating. Reactors are used to turn gas into methanol, while heat exchanger and separator help control temperature and purify the product. Mass and energy balance are used to keep the process safe and efficient. While fluid mechanics help us move gases and liquids through the plant, it is used to design pipes, pumps, and compressors so that everything flows smoothly. We also study how fast the fluid moves, how much pressure is lost in the pipes, and how to keep the system working properly. This ensures the plant runs safely and save energy. As we can see below, this is the sum of the formula that we will use for the calculation in this project. For the first one is the sum of the molar flow rate in equal to sum of the molar flow rate out. Then for the next one is the enthalpy change. And then the next one is Reynolds number, used to determine whether the flow regime, whether it is turbulent or laminar. And for the last one is the pressure drop.
Hello, my name is Ezra Daniel Bemazli. So here is our plan. So this is the diagram for our reactive system and non-reactive system. So for the first mass balance in reactive system, we have two reactions involved, CH4 plus 1 over 2 O2 and CH4 plus H2O. So we get CO and H2 in the output. So our composition for the output is CO2 0.1129, for the H2O is 0.1174. For the CO is 0.2558, while the H2 is 0.4839. For the mass balance in non-reactive system, molar flow rate for feed is 113.03 kilomole per hour. So all the composition for methanol will go to the top product, and all the compositions of water will go to the bottom product. So the top product will get 70.32 kilomole per hour, and the bottom product will get 39.71 kilomole per hour. So here is our energy balance in the reactive system. So in our table, we will have H1 until H9, but H1 is until H4 is zero, since it is our reference state, which is our lowest energy. So here is the coefficients for A, B, C, D, and then we get the total and heat of reaction is negative 81,000 kilojoule per hour. Here is our energy balance in a reactive system. So I made a table which contain methanol and water and in and their H out. So the reference state is methanol and water in liquid 180 and 40 degrees Celsius. So since methanol will go on vaporization, so we will consider the latent heat of methanol. So after the calculation, we get the total heat of reaction is 13,000, around 30,000 megajoule per hour.
I will explain our pipe layout and the pressure drop calculations. We select stainless steel as the pipe material because of its high corrosion resistance, durability, and suitable for our both water and methanol process. The pipe diameter we use is 2 inch, which is balanced for both flow capacity and pressure control. For fittings, we assume 90 elbows since they are commonly used in chemical plants. As for pipe length, we estimate range between 10 to 20 meters, depend on each segment for the plant layout. As we can see the pressure drop calculations on the right side, we consider the Reynolds number, friction factor, and calculate the pressure drop for each pipeline. After summing up all the individual drop, we obtain a total pressure drop of 144.9229 kilopascal.
Now I will explain pipeline calculations using pipeline 1 as an example. First, we'll look at the process diagram to see where the pipe starts and ends, what gases are inside, and what the temperature and pressure are. For pipeline 1, the gases are CO2, CO, and O2. The temperature is 600 degrees Celsius and the pressure is 25 bar. We calculated the gas mixture's density using the ideal gas law and the viscosity based on the temperature. Then we find the Reynolds number to determine if the flow is turbulent or laminar, followed by the friction factor using a specific formula. With this, we calculated the pressure drop inside of the pipe. Pipe 1 doesn't require a pump, but for the pipes that do, we estimated the pump power using the pressure drop, flow rate, and assumed pump efficiency of 70%. For pipelines, after the separator, we used a slightly different method due to the phase and composition changes. All formulas, calculation, and steps you can refer to our slides or report. Thank you.
Now let's look at pipeline 9, which is connect the gas liquid separator to the distillation columns and handles a liquid mixture of methanol and water. Step first, we need to calculate the mixture density using mass fractions and individual densities. Step 2, we will find the volumetric flow rate, which is Q, and convert the mole fraction to the new mole fractions based on molar flow and calculate the average molar mass to determine mass flow rate. Step 3, we need to calculate the Reynolds number using the formula. And for step 4, we will calculate the Darcy friction factor using the Blasius formula. Finally, we will substitute everything into the pressure drop equations, and we will get our pressure drop, which is 395.58 Pascal.
Okay, next I'm going to explain about the main products delivery. Since we are using methanol, which is a volatile and highly flammable liquid, we choose to use the stainless steel for our piping material, and the other details include the 2-inch Schedule 40 and also the 90-degree long radius elbows. Basically, we choose to use the stainless steel because it is known as its ability to withstand the high operating pressure, as we use the 80 bar here, and also at the same time it is best and excellent for the chemical and corrosion resistance, as it is very good to handling the gas mixture that contain the corrosive components such as the carbon dioxide. And then the other thing is about the safety. Basically, we choose to refer to the American Petroleum Institute in year of 2020, where the other details that need to be implemented for our tank design basically is the ratio of the height and also diameter from 1 to 1. So basically, from that information, we can actually estimate our value for the diameter and also height for our tank. So, and the other thing I would like to highlight here, which is about the safety, since it's very crucial for our plant design. Basically, the first one is, as I've been mentioned, which is the tank design. So basically, tank design account for significant thermal expansion of gases with temperature changes. So it's very crucial for to prevent over pressurizations. And the second one is we use the inert gas blanket using the nitrogen. So it is very important to mitigate the risk of oxidations of our gas flow. And then the third one is we use the gate valve. So it is very important since it is crucial during the emergency situation, so that we can actually control the flow and for effective isolations. And then for the storage tank details, so basically we need to calculate first the pump work. So basically we calculate the work for our pump by using the formula using the information of the molar flow rates, the pressure drops, and also the density of our methanol, which is around 755. And then we choose to use the efficiency of 75%. So basically, using the information, we can proceed to the next calculation where we know about the volumetric flow rate, and then we try to estimate it to use for 3 days. So basically, we times it with 24 hours and then times it with 3 days. So basically, that's the volumetric flow rate that we get, which is around 223 meter cube, and then by the information, we can know the maximum methanol to be filled in our storage tank, which is we estimate it to be filled around 80%. So that is very important. So the methanol is not overflow. So basically, after that, we know the volume of our storage tanks, which we divide with our filled methanol around the 80% that I mentioned just now. So basically, using the formula of our volume for the tank, so we can directly know from there what is our diameter and also height for our tank, since I mentioned that we followed the API, which is around the ratio of 1 to 1. So basically the height there we can replace it with the value of our diameter. So basically we get our diameter and also height around 7 meter. And the next one, I would like to highlight about the room for the improvement for our plan design. So basically, we need to always make sure that proper maintenance are always being taken care of, and also at the same time we need to try to minimize the pressure loss so our products can be more optimized. That's all.
So, in conclusion, the methanol production process demonstrates how co-chemical engineering concepts work together. Principle of chemical engineering help in designing and analyzing reactors, separators, and heat exchangers using mass and energy balance. Meanwhile, chemical engineering fluid mechanics ensure efficient fluid transport through proper flow, pressure, and pump design. Together, these principles enable a safe, efficient, and practical methanol production plant design. That's all from us. Thank you.